All right, today we're jumping into one of my favorite and honestly one of the most elegant ideas in all of algebra, inverse functions.
You know that feeling when you're deep into a math problem and you just wish you had a giant undo button? Well, guess what? In the world of functions, you kinda do. And yeah, that's exactly what an inverse function is.
So let's break it down. What is an inverse? Well, at its heart, it's all about reversing the process.
And the core idea? It's actually super simple. Imagine a function, we'll call it f, is like a machine. You put x in, and you get y out. Well, the inverse function is the machine that does the exact opposite. You feed it that y, and boom, it spits your original x right back out.
Okay, so here's the formal definition, and you've got to pay attention to the notation here. When you see that little -1, that is not an exponent. I repeat, not an exponent. It's the special symbol we use for an inverse. It's our official mathematical undo button.
And this undo idea leads to a really cool consequence, a complete swaparoo. Everything that could go into your original function, its domain, becomes everything that can come out of the inverse. That's its range. And vice versa. The original outputs become the new inputs. They literally just trade places. Seriously, lock this idea in your brain, because it is absolutely crucial for everything we're about to cover.
Okay, seems simple enough, right? Just reverse everything. And you knew there was a but coming. There's a catch. Turns out, not every function can just have a simple inverse. There's a very important rule it has to pass first.
So, the big question is, does every single function out there have this nice, clean inverse? And the answer, which might surprise you, is a hard no. To see why, we need to dig into a special property that only some functions have.
And that special property is called being one-to-one. Now, what does that mean? It means that for every single output, every y value, there is only one unique input, one x value that could have made it. You can't have two different inputs that lead you to the same exact output. Each output has one and only one origin.
Now, you could try to figure this out with a bunch of algebra, but who's got time for that? There's a way better, much faster way to check. It's this awesome visual shortcut called the horizontal line test. Okay, look here. On the left, we've got our classic parabola, x squared. See how if you draw a horizontal line, it can hit the graph in two spots? That's a fail. It means one output, like y equals 4, comes from two different inputs, x equals 2 and x equals -2, not one-to-one. But now, look at the cubic function on the right. Try it. No matter where you draw that horizontal line, it only ever crosses the graph once. That's a pass. This function is one-to-one.
Okay, so now we know what an inverse is, and we have a test to see if a function can have one. So how do we actually find the formula for it? Let's get our hands dirty with the algebra.
Believe it or not, it's a pretty simple two-step recipe. First, you take your function, y equals f of x, and you just do some algebra to solve it for x, get x all by itself. Then, step 2, once x is isolated, you literally just swap the letters x and y. That's it. Your new equation is the inverse.
Let's actually try this out. We'll use a nice, straightforward example. F of x equals 3x minus 4. So the first thing we do is just rewrite it as y equals 3x minus 4.
All right, step 1, solve for x. To get that x by itself, we'll add 4 to both sides. That gives us y plus 4 equals 3x. Now, we just divide everything by 3. And there we go, x is all alone. Okay, and now for the easy part, the final step. We just swap the variables. Where you see x, write your new y or f inverse, and where you see y, write x. And that's our inverse. The inverse function is 1/3 x plus 4/3. Done.
Okay, we've crunched the numbers. But now let's get to the really cool part, the visuals. Because when you graph these things, the connection between a function and its inverse is, well, it's actually really beautiful. From a geometric point of view, the relationship is just stunning. The graph of an inverse function is a perfect reflection of the original graph. And what's the mirror? It's always that perfect diagonal line, y equals x.
Just look at this graph. The original function is there in blue, and its inverse is in orange. See that dashed line cutting through the middle? That's our mirror, y equals x. And you can literally see how, if you were to fold the paper along that line, the blue and orange curves would match up perfectly. They're perfect mirror images.
Okay, that's great for functions that pass the test. But what about the ones that failed? Remember our parabola. The functions that weren't one-to-one. Are they just out of luck? Well, no. Turns out there's a very clever workaround. Let's circle back to our old friend, the parabola, y equals x squared. We already know it fails the horizontal line test, right? As a complete function, it can't have a simple inverse. Why? Because you get the same output from two different inputs. It's not one-to-one. So how do we solve this? Well, if you can't follow the rules, you change the rules. Instead of trying to find an inverse for the entire function, we can do something called restricting the domain. Basically, we just choose to look at a piece of the function, a piece that all by itself would pass our test. And here's what that looks like in practice. See on the left? We're just ignoring the entire left side of the parabola and only looking at the right half, where x is positive. Now, does that piece pass the horizontal line test? You bet it does. And its inverse is the positive square root of x. We could do the same thing for the left half, and its inverse would be the negative square root. By splitting the function, we found a way to make it work.
So let's wrap this all up. An inverse is math's undo button. It swaps your inputs and outputs. And while it technically only works for one-to-one functions, we saw that if a function fails the test, we can get clever, change the rules by restricting the domain, and make it work anyway.
And that really brings us to a bigger idea, doesn't it? We saw a rule that said, no, this function can't have an inverse. But by thinking a little differently, by changing our perspective, we found a way to make it work. So the next time you're stuck on a problem and hit a rule that seems like a total dead end, just ask yourself, is there a clever way to bend this rule? Thanks for diving in with me.